Seen the boundary layer equation that we derived. By solving that, we can get our laminar mean flow. Now here we are starting with the stability formulation. So we are doing the stability analysis for the incompressible boundary layer. So these are the incompressible Navier-Stokes equation in non-dimensional form. So the first here we have continuity equation, then momentum equation in the x direction, then momentum in y. As you have noticed when we was talking about the derivation of laminar Blasius equation, there we consider the momentum equation in the y direction is just the gradient of p, since our v velocity in the boundary layer are 0, so these all terms has gone 0. But here we are starting with this full x momentum equation, and we will see that as we go further down there is the assumption of considering since there is no wall normal velocity, so that is eventually going to be 0. So here r is the Reynolds number based on the free stream velocity and the flat plate length. For simplicity, we rewrite the above equation. The continuity we denote as a ux, since the derivative is with respect to x and v with respect to y. So we are rewriting the same equation in a simple form where the subscript is denoting that this particular variable is being taken derivative with respect to the subscript. Now if we consider the instantaneous flow variable, that can be decomposed in terms of the mean and the perturbation. So here we are denoting the mean as a bar and perturbation as a tilde. We are not denoting as a perturbation as a prime, since we use the prime for the derivatives. So we can decompose each of these instantaneous flow variable in terms of the mean and perturbation. And since we show earlier that in the boundary layer there is no wall normal velocity, so this we assume over here that there is no wall normal velocity, and we can neglect this mean wall normal velocity as a 0, so this will just instantaneous is just a perturbation. So in the boundary layer flow, so this is the same thing. In the boundary layer flow, mean wall normal velocity is 0, so we are setting the v bar as a 0. And the linear stability assumes that there is a surface parallel flow, so this component mean velocity of wall normal velocity will only come when there is a non-parallel flow, but the linear stability assumes that the surface parallel flow, so we neglect it. Though this is not always the case where the flow is always parallel to the surface, when we have some curvature shaped body where we have the wall normal velocity component, and for accommodating that non-parallel flow we have the different theories. That is non-parallel stability theory, we call is a non-linear PAC. Then non-parallel PAC that account for this the wall normal velocity as a non-zero. So this is the important step over here. Upon substituting the above definition of instantaneous flow variable given by equation 4, which is over here, this is the instantaneous flow variable, into the governing equation 1 to 3, and subtracting the mean flow equation from the stability from the resulting equation gives this particular equation. So when we substitute, when we have this 3 governing equation and these are the instantaneous flow variable equation, when we substitute this in over here, and since these equations will also satisfy for the mean flow, so when we subtract the same equation for the mean from the instantaneous, we get the 3 set equation that only deal with perturbation. So we have the mean variable also here, but now this equation is mainly in terms of perturbation. Now in this equation, when we look into different terms, we see that we see there are some terms where the perturbation is being multiplied with the perturbation itself. So those are the nonlinear term. So we see these two terms are nonlinear in the x momentum, and these two terms are nonlinear in the y momentum. Since we are dealing with only the linear stability, so for now we will neglect this equation. Neglect these terms. If we want to look into the nonlinear term, we can consider this, but further we will have to find a way to model this term. So for now, we are dealing with the linear stability, so we will neglect these terms in these two equations. So after neglecting the nonlinear terms, our equation is reduced to this three equation corresponding to the continuity and x momentum and y momentum. Now looking at this equation, we have to ask a question that we have three equations. Is it possible to reduce this system of three equations to one equation? If we can reduce the one equation to one equation, we will have to solve only one equation. But is it possible? Because solving all three equations is going to be a complicated task. So can we reduce it to one equation? Now, if we start looking into this to reduce into one equation, we have to look into what is the common variable which is in all these three equations. So we are looking into a system of equation which is in terms of perturbation. So we have when we decompose our instantaneous flow variable over here, we had three perturbation: u perturbation, v perturbation, and p perturbation. So is it possible, like what kind of perturbation is available in all these three variables? If we look at the continuity, we see the u perturbation and v perturbation, but there is no p perturbation. So obviously the continuity equation cannot be expressed in terms of p perturbation. If we look at the x momentum, here we have the u perturbation, v perturbation, and p perturbation. So this can be expressed in either of these three. Here when we look at in the y momentum, we have the v perturbation and we have the p perturbation, but not u perturbation. So this can be expressed in terms of v perturbation and p perturbation. So what we find that in this all three equations, there is v perturbation. So isn't it possible to reduce this all three equations into one equation that deal with only the v perturbation? Because v perturbation is present in all these three equations, so it is possible to express all these three equations in terms of v perturbation and then substitute in each other and express these three equations in terms of one equation. So that is what we are going to do to reduce this three equation into a v perturbation equation.